Now, in the previous section, we explored the differences between non-living objects and living substances. Something they both have in common is that they are both composed of certain elements, and these elements are present in both of these images that you see over here. Look at the beautiful colors that are shown on the parrots, and the abundance of oxygen, nitrogen, carbon, hydrogen, nitrogen. Over here we have silicon, and in the beginning we have sodium, iron, calcium, and potassium. These are just some of the elements that are present in both kinds of objects. So it's very important to study a basic chemistry before we go on to a biology class. I know that you're in a biology class, but we will explore some of the fundamental basic chemistry to explore and understand some of the concepts that are applied in biology. Elements are basic substances. Elements, these basic substances are present in three different forms, and those we call as matter. So matter is defined as anything that occupies space and has a mass. Two very important criteria: mass and space should be present for identifying anything that is matter. Matter is present in three different forms: solids, such as a chair or a book or a brick; liquids, such as water or acetone or alcohol; gas, such as carbon dioxide, oxygen, or chlorine, or methane. So they're always going to be present in three different forms. All matter is going to be composed of the basic substance, and those basic substances are elements. There are 92 of these naturally existing elements. There are always come up with some new elements. If you look in a periodic table, you will see some elements that are written beyond the number 92, and those are human-made or man-made, and they're not biologically important, so we're not going to go into a depth for those elements. The basic elements for life are these that has an acronym down here. C is carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Let's see, there is sulfur. So these are the six basic elements for living that are present in living cells. Besides that, a small amount of sodium, potassium, magnesium, calcium, traces of iron, and sometimes manganese are also present in some certain cells. Now these elements are arranged in a table which is called as a periodic table. A periodic table is a very well designed chart which represents certain properties of elements, whether they are in a horizontal period or whether they are in a group which is a vertical column. So if I pick a column like this, then they have something in common. If I pick a period like this, then these elements have something in common. So coming back to another vocabulary word, what are atoms then? Atoms are the smallest part of an element. So for example, if I was to take a piece of iron, the symbol for iron is Fe, and I take this small little piece and hammer it down. The smallest little particle that will still exist a magnetic property, because that's one of the properties of iron, that it conducts magnetism. That would be an atom. Atom of every element has been given certain important characteristics. Atoms usually have a symbol. The symbol of an element can be either a simple letter such as C, that is represented for carbon, or it can be, for example, H for hydrogen, N for nitrogen, O for oxygen, Na for sodium, Mg for magnesium, Cl for chlorine. Notice that either if I use one letter, it's always uppercase. If I use two letters, the first letter is uppercase and the second letter is then a lowercase symbol. So most of these elements have a symbol and they're given in the periodic table. And the one that I just named you, those are the ones that you really would need to know for biology classes. Each atom has subatomic particles. And the number of subatomic particles is represented in these two vocabulary words. One is atomic mass, which is the larger of the two numbers that are written next to an element's symbol. The number that is the smallest is the atomic number. So here the number is 6 and this number is 12. Weight and mass is slightly different when we talk about this, and I think I'll mention it later to you once we do talk about isotopes as what is the weight. So right now let's use the term atomic mass. Atomic mass is actually depicts the number of protons and neutrons that are present within the nucleus. Notice the three particles that are present in the atom are shown over here. Notice the size of these two particles are larger, and that's the one that's present in the nucleus. So that constitutes the mass, which would be, the mass would then be the total number of protons plus the total number of neutrons. However, the atomic number is the number of protons only. The atom is always neutral. So because atom is neutral, we will find out that the proton is a positively charged particle. So in order to have a neutral charged particle, the negative charged particle must be of the same value. So the number of proton equals the number of electrons. So from any given information of atomic mass or atomic number, you can find out as to the number of protons, neutrons, and electrons for each. So let's just do a few examples. For example, for oxygen, the number on the top is 16 and the one on the bottom is 8. So this means that the oxygen atom would have 8 protons, 8 electrons, and the neutrons would be 16 minus 8, and that is also 8. For example, if I was to do sodium, the sodium has the number, I'm going to write down 23 as the atomic mass, and the atomic number is 11. So if I was to do the same breakdown, protons would be 11, electrons would be 11, the neutron number would be 23 minus 11, and that is 12. So this is how you would find out the number of the subatomic particles for each atom. A lot of times, instead of calling an atom of an element, which is a really tiny particle, the expression is used, which is the mole. A mole is an expression like we use when we call the term dozen. The term dozen implies a certain number. So whether when you're talking about a dozen roses or a dozen pencils, you can visualize that there are two different objects, but what is common is the number. A mole is just a standardized unit that is also used in the same way, and a mole is however a very large number. It's a number which is equal to 6.023 10 to the power 23. So if I was to remove the decimal, you can imagine this number is going to be 6023, and then I would keep on adding 21 zeros total, a very large number of quantity. So here is an image that shows a mole of soccer balls, a mole of softballs, and here is a mole, and I really don't know if these are small pebbles or small. It looks like marbles or ball to me. What is common is that they all have the same number of quantities, and the quantity in each I think is 12, but you can see that the size is different. So if I say a mole of, for example, H2O and a mole of, let's say, another molecule that is glucose over here, then a mole of glucose and a mole of water will have the same number of itemized quantities of atom, but the masses would be, however, different. What are isotopes? Isotopes are variation of atoms, and they differ in the number of neutrons. So for example, in the previous example when we did carbon and we said there were 6 protons, 6 neutrons, and 6 electrons. And this was how it was written down there. So now if I change the number of neutrons and we say that the number of neutrons are 6, but the number of protons are 6 still, the number of neutrons are 7, and the number of protons and electrons are 6. So the atomic mass would now be 6 plus 7 would be 13, but the atomic number would still be 6. And if we have another variation in which we have 8 number of neutron, that would change, and it would be carbon 14 on the top and 6 on the bottom. Now these isotopes are variations of atoms. They have the same atomic. What do they have something in common? And this number is called as the atomic number. So they have the same atomic number. They have different atomic masses. So when you take the average of all these masses, the average of all the masses are then expressed in the term weight. So when we say atomic weight, we are looking at the average of all the atomic masses of all the isotopes of that element. So it's a small little difference between the term between mass and weight. For simplicity for this class, whenever you see a fraction written on a periodic table, just round it off to a whole number. Isotopes are very important for tracer studies. So whether it's getting a CT scan or whether it's checking for your thyroid, it's a radioactive. Isotopes are usually radioactive, which means that they emit certain forms of radiation. And these radiation can be used to depict certain cancers or certain pathways within systems. So let's look at the last slide on this section, and this is the how electrons are arranged in an atom. Now the electrons are arranged in an atom firstly around the shell. And the shells of an atom is the region that is shown as a planetary model. This planetary model was devised by Bohr, so it's lots of time it's referred as the Bohr's diagram or the Bohr's model, in which we can see that the nucleus is the central core like the sun, and you can see the orbits or the planets that are revolving around it. Each shell that is around the nucleus has a fixed number of or a maximum number of electrons that it can hold. The first shell can always hold up to 2. The second energy shell can hold up to 8, and the third can also hold up to 8. So anytime if a shell is not holding that maximum number, think of that shell being a vacant. For example, in this example of hydrogen, we see there's only 1 electron. So hydrogen, the first shell can now take 1 more electron because it has a vacancy of 1. Carbon, over here you can see there are 4 electrons in the outside shell. Because the total number of electrons for carbon is 6, and they will distribute as 2 and 4. And the first 2 go into the first 2 shell, and the 4 goes on the second. So now the vacancy for carbon is 4. Nitrogen, the total number of electrons are 7. I'm hoping you're getting where I'm getting this number from. This is the atomic number that I just showed you previously to determine. So coming back to nitrogen, you got the first 2 here, and then you have 5 in the second shell. So you've got a breakdown of 2 and 5. So now you have a vacancy of 3. Atoms will bond with each other based on the vacancy that they have for each shell, and there is a rule that helps them bond, and that is called as the octet rule. Octet comes from the term 8, except for the first one. We can see an exception over there, but generally the magic number is 8. It must complete a shell to have 8 in it, except for the first shell that can only hold 2. So many bondings that we will look at later on, which is bonding means how electrons of one element combine with another electron of another elements, and when two or more atoms bond together, we call this as a bond, and they form a molecule. So atoms would be singular, if you can think of it this way. If you have an element, it's breaking down its atom, just one piece. When you put two or more atoms together, they form a molecule.